Okay, thanks everybody for joining us for the last session. And I guess we'll get started with Kris Hauser representing DRC-Hubo. Thank you very much.
All right, thanks everyone for coming here after your coffee break so promptly. So my name is Kris Hauser. I was one of the team members on Team DRC-Hubo. I'm representing Paulo, who's the lead on this project. Good to be here. I'm from Indiana University. Shortly will be at Duke, and I'll try to talk about. So DRC-Hubo did not pass the top cutoff in the DRC trials, and I'll try to talk about why that was the case, what went right, what went wrong, and what we can learn from this experience. So for those of you who have not been to the country trial events, Team DRC-Hubo was a pitch to use this kind of resource that we have in the U.S. We have several of these humanoid robots, Hubo, that were supported by an NSF, large NSF grant. They were brought over from Korea by Paulo in partnerships with Juno and others at KAIST. And the idea was to take these many Hubos and essentially sort of crowdsource the engineering of these different DRC events. So we could take domain experts in each individual task, have them work on a Hubo, and then apply them to each of these individual tasks. So there's a lot of many different universities that were involved in the project. Drexel was the lead. We had Delaware, Ohio State, KAIST, Georgia Tech, WPI, Swarthmore, Indiana, Purdue, and Columbia. So this is actually a really humongous team. We had something like 50-odd students and grads and postdocs and professors working on this project. So one question to ask is, well, how do you organize such a large team? And the idea was that what we could do was kind of divide and conquer the DRC tasks into smaller groups that could focus on the specifics of each individual task. So the lead for developing software was, well, Drexel was the kind of ringleader. They collaborated with KAIST to build the hardware of the Hubo and make upgrades to the Hubo hardware for the DRC tasks. And the idea was to take the different regions of the US that were represented by our teammates and do prototyping on each of the Hubos that were in these regions. There were 7 Hubos altogether. 4 of them were in the Northeast, 2 of them were in the Midwest, and 1 of them was at Georgia Tech. So we have a variety of different people involved in this project. And let's see. So we eventually found out that the Hubo robot that was already existing in the U.S. was not sufficiently capable of performing most of the DRC events. We performed extensive simulation trials, and essentially we made some recommendations that were taken into consideration by KAIST. They provided this nice upgrade to the Hubo robot to produce DRC-Hubo. It had longer and stronger arms. It had an extra degree of freedom at the wrist, so 7 degrees of freedom on each arm total. Pretty strong hands that were able to hold 10 kilograms, and also a sensor head with better sensors than the original Hubo robot. So one of the issues that this brought was that this is a pretty significant upgrade to those Hubos. We were not able to actually procure 7 upgrades to all those Hubos. Instead, we were only able to produce 2. 1 at Georgia Tech, 1 at Drexel. So even though we had this kind of distributed approach, we were able to we actually were able to simulate, in some sense, the environment of the DRC trials a little bit more faithfully than maybe some other teams that had people situated in direct line of sight with the robot. We actually had to SSH in, we had to connect into the remote site at Drexel and actually try to get a real sense of communication latencies, communication bandwidth limitations, and so on, lack of situational awareness, and so on, to actually control this robot in our what we call the boot camp. So we set up several mock-ups in Drexel. We had several students. We had, I think, around 20 students who went to Drexel and actually took place in this. Paulo is really a fan of putting sappy music to his videos. But you can see we have mock-ups for all of these different events. We have we had a golf cart, we had a ladder, we had valves, etc. All in this big warehouse we had a command trailer, etc. And we were able to spend the entire summer working on these, working on the actual hardware, and then practice afterwards using a remote teleoperation. So let me skip ahead to some of the. Okay, so we had this phase near the end of the project, the validation phases were these mock trials where we really tried to simulate exactly what we would see in the DRC. So we actually had people in the command trailer try to teleoperate the robot, or to be in a remote location to teleoperate the robot at Drexel. And so with this this kind of setup, we were pretty confident that we'd get around 12 points. We were able to test for several months, I think 2 months of straight testing, and we would get optimistically up to something like 14 points. And in our least optimistic estimate, well, sometimes the robot would break and we'd get 0 points. But in any case, if everything went well, we thought we'd get probably around 12 points. Here's just an example of why we were so confident. So we were able to, this is our mock-up of the valve turning event. This is the WPI is the lead on this effort. This is Dimitri Berenson's work, and also Jim Main-Price is the postdoc on this. It took a little bit of time, 29 minutes, but basically everything went flawlessly inside our mock-up environment, and so we're pretty excited by this, and also the ladder climbing event. We thought we'd get full points on. So let's see what happened when we actually tried to put this into practice. So day one of the DRC, we had the kind of more extreme locomotion tasks. So we had the vehicle, the terrain, and the ladder. We thought that optimistically we'd be able to drive across to get the one point of the vehicle. We had a couple of snafus with the whole setup. As you all know, that this was a very hectic kind of event, and we had an accidental e-stop, which caused us to have to redo this trial. The robot drove around halfway. They were trying to get more situational awareness, and because of some weird thing about a cable, they actually snapped the cable halfway through, and then they ran out of time and got 0 points for the vehicle. In the terrain, there was an operator error, and the robot fell. And the ladder, kind of shockingly, so we were the first team to actually try to do more than 1 point on the ladder. We reached the top step and fell. So this was a pretty neat result. We thought we'd be able to get all the way up to the top. Our robot did pretty darn well. It kind of went slow but surely. And what you can see is that right when right about here where the camera pans away, there was a slip of the finger, and the operators did not catch it. And everything went well for another step, and then once they tried to release the other hand, this dramatic thing happened. So we were bummed, but we did pretty well. 8 out of 9 steps wasn't bad, and so we're pretty happy with our performance. Okay, so the next day we had these manipulation events, and kind of disappointingly, we had only 1 point on all of these events. It was actually quite frustrating for all of us to watch our robot just kind of take a few steps and sometimes just fall without doing it. We had a few other snafus. We had an issue with the valve turning halfway through when the hand kind of knocked the robot over through. And because of slight unevenness of the ground that was given in these events, the robot fell over because it was doing open loop control. So that was a huge problem. So we got 3 points, and basically that's the end of DRC-Hubo. The question is, well, what did we learn from this process? So first off, I think, in my opinion, one of the first lessons from this project is that, well, our team just had some essential problems. First of all, event by event breakdown, in my opinion, from the beginning was a bad idea. So I think, robotics is an integration problem. We need to have people kind of vertically integrated from controlled perception to high-level planning to user interfaces and so on. We have dedicated people for each of these. For example, one issue that we had is that we had no balance control. That, to me, was a critical blind spot of our team. So to handle wind or unevenness on the ground, we had absolutely no ability to deal with that. We had no expert to deal with teleoperation, so that when our planning failed, we couldn't recover. We had no perception expert, so we couldn't build 3D maps of the environment and try to recognize objects. And frankly, our teams, our sub-teams, had uneven expertise and also different visions for how the events would go. So this is kind of a big issue. Having these huge distributed teams with a variety of expertise is, in my opinion, quite a bad idea. We also had pervasive hardware issues. Things would kind of arbitrarily break. All of you had hardware issues, but I think DRC-Hubo had a little bit more than the average. And one of the other critical flaws is that we did not have any dry runs with the network limiter until 2 days before the trials. And so teams that were hoping to do teleoperation or hoping to get point cloud streams from the camera at a certain rate were just completely shocked and scrambling until the very last minute to try to fix their systems. So this was a huge oversight that could have been avoided. Lesson number 2. This is not our teams, it's not team specific, but I think this is a lesson that applies to everyone, and I've heard it repeated here several times. But whole body locomotion with contact is still an unsolved research problem. We're getting closer and closer to being able to solve it, but we're not quite there. So if we look at the point performance of these 4 types of robots, I'm eliminating Hubo in this plot, we see that the places in which very few places actually scored highly on are, well, the vehicle, and also, so the ladder too. So Shaft, I'd say, got 4 points on climbing stairs because they climbed without handrails. So I think that's a little bit unfair. The other Hubo team got 4 points on the ladder, but it seems like we're having huge problems getting full points on the ladder and also the vehicle. So this led a lot of team strategies to just get a single point on the ladder, to get a single point on the vehicle. Also, by the way, this whole vehicle ingress and egress task, I mean, hypothetically, ingress should be the opposite of egress, right? So if we're going to be able to do egress, we should probably be able to do ingress just as easily. But we're essentially cheating on this problem. I mean, if we really want to solve full body contact, we should be able to do ingress. So I think that we're kind of only half addressing this problem of full body locomotion. So just a little bit of the details of what went right on our ladder climbing event. So this was between me and George Lee at Purdue. We shared this event. Our approach was to essentially do full autonomy, almost full autonomy with human checking. We were also, we had the system built so that it can handle essentially any ladder. So these are the 2 philosophies that we took from the very beginning. So we were able to show that we had a planning approach that was able to take any kind of model of ladder and try to plan a path for it. Sometimes the path would succeed, sometimes it would fail. But we found that this DRC-Hubo robot could climb ship ladders with and without rails, vertical ladders, as well as A-frame ladders. The planner that we developed was very fast, so we were able to plan in about 15 seconds or so, all the way from the bottom of the ladder up to the top of the ladder. The role of the human would be to check to see that each step is being performed as it's supposed to, and then to stop the robot if it needs a refresh, it needs to be adjusted, and then the planner will then replan from the intermediate step in which it's stopped. So this worked pretty well. The planner that we had was a motion primitive-based planner. So we had primitives that were designed for a kind of nominal ideal ladder. So for example, placing a foot on a higher rung, moving a hand to a higher rail, etc., shifting the center of mass, etc. And online, for any new ladder, we would take that primitive and try to produce a feasible path in the new environment that's close to the original path. The way that we did that was with a sampling-based technique, and using sampling-based planning, we were able to achieve greater reliability than other techniques like warping, while still retaining essentially the flavor of the initial path. So the planner is pretty robust. So given a single motion primitive for a ladder with a certain inclination, that's the x-axis here, and a certain rung spacing in the y-axis, we're able to take that primitive, the set of primitives, and adapt it to kind of this range of rung spacings and inclinations. So it's about 72% of these ladders. So we can't do vertical ladders with short rung spacing because it turns out that the ankles are about 20-something centimeters high, so we're not able to kind of fit them between the spacing. And we're not able to achieve really, really high vertical ladders because the knees have to be pulled up too high. But you can see this is pretty wide coverage with a single motion primitive. We're also able to test our controller pretty robustly in simulation. So we developed a compliant arm controller that tolerated errors in the hand placement as long as the rail was within the finger range, as long as it was able to eventually kind of conform using this compliant controller to enveloping the rail. It was able to hold on securely. We're also able to see about 2 centimeters of variation in the vertical position of the rung, and that should be tolerated by the robot. We also tried to push the robot as it was climbing the ladder, so we dropped objects of increasing mass onto it. So we have a 5 kilogram mass, there's going to be a 10 kilogram mass, and it still stays stable. And then finally, in 15 kilograms, this is where we stopped, so you can probably imagine what happens here. The robot falls. But we thought this was a pretty good result. Okay, so lesson number 3 is that it is really critical to have robust dynamics and context simulation tools, especially when you're doing full body locomotion. So up here you can see a built-in collision detection module from the Open Dynamics engine, where an object with 0 coefficient of restitution just bounces uncontrollably perpetually, which is not realistic behavior. Let's see, I believe this is actually a typo. This is actually from Track Labs. This is the valve turning task, and for some reason, the gazebo simulator just explodes for no apparent reason. We also tried to do gazebo on Hubo, and this is the result that we got. He's about to land. Let's see. There he goes. So pretty unrealistic behavior, in my opinion. So it turned out that I had been developing a simulator that I never thought that people would want to use because I thought everyone had great simulators, and so just recently we released it. This is the one that is used in all of my simulation videos. It's called Clamped. It's been tested and used for 4 years. It's based on OE with some custom contact handling mechanisms that turn out to be much more stable, produce much more stable contact estimates than Bullet or OD's built-in. We're able to do manipulation tasks with, these are just raw triangle meshes simulated against triangle meshes. There's no need to define collision primitives and so on. It has APIs in Python and C++, and there's a variety of different projects in which this was used, including throwing, walking, ladder climbing, as you've seen, and also simulating force sensors. So we validated the output of the simulator's force sensors to the actual robots with some pretty decent matching. Another thing that I'm really excited about is that we can take raw sensor data, mesh it, and then throw it into the simulator. You get these really disgusting looking meshes that are just, they're thin shells, they're only seen on one side, and they're noisy and horrible, and any other simulator would not be able to touch these things. But yet we're able to simulate crawling on these meshes with no problem, no tuning whatsoever. So this is close to 500,000 triangles, and simulation is completely stable.
What simulation rates are you getting with this?
It's pretty slow. It takes this one in particular. This is 1 million triangles. It takes about 30 seconds per frame at 30 frames per second. So it's definitely an order of magnitude slower than real time, depending on the complexity of the terrain. So yeah, here's a step ladder example as well. So those are okay. Final lesson is that robots are slow. How many of you were just so excited to watch these robots just stand around for half an hour and maybe do something with no warning? So there's kind of an X factor that's coming out of the DRC, and that's, well, how many times are your robot videos sped up? So let me see if I can get this sound here. So this is ISMC's music. This is from, I didn't put this on the video, this is what they put on their video to demonstrate their Alice robot. So they decided that the most appropriate music to put onto their video was elevator music. So it's like watching our robot is just as exciting as waiting in an elevator. I think this is a really huge problem. I think we need to be spending the next 5 or 10 years working on speeding up our robots. And it's not just faster computation. We can have planning in 15 seconds to climb up a ladder. Planning time is not the problem there. So I would say that the bigger problem is handling dynamics. So generating geometric paths is pretty easy, but if you just execute these directly, you have problems like this where your robot can very easily tip over. So people end up executing their motions very slowly. So I've been working a little bit on trying to address this problem. I have a very fast trajectory optimizer that takes an initial path and then optimizes the speed along that path. It's very robust. It works on complex optimization principles and basically can optimize paths for 100-degree of freedom robots in just a couple of seconds. Here's an example of a motion with contact. These two blocks are balancing on this other block, and it's able to optimize so that the accelerations that are felt by the block don't cause it to tip over. So if you're interested, you can go grab it at this website as well. Okay, so current research directions. All of us who have worked on the DRC are basically working on other topics right now. I in particular am interested in this robust simulation topic with raw sensor data, and also working more on the full body locomotion problem. I think we can, with several years of work, we could probably get to real-time optimization with motion primitives and fast trajectory optimization to the point where we could probably, optimize a recovery motion for pushing an object, pushing the robot sideways in an unstructured environment. I think we could probably do that within a few years of effort. I'm open to collaborations. I think that I really like I like that several people here have released their software open source. I think we should do more of this. I think we should encourage this. Perhaps there could be some kind of common repository for all this work, and somebody could try to work on organizing it and curating it. Maybe something like an open DRC sort of repository. So this is an idea to throw out there. So, and that's it for my presentation. I'll take any questions. I'd like to thank these collaborators and DARPA for funding the DRC effort. Thanks.
Any questions for Kris?
So we got the ladder planning part. Were there other, you were lacking expertise, the team was lacking expertise in other things. Were there other strengths of expertise?
So, Dimitri Berenson, who worked on the valve turning, he worked on a pretty similar approach to what we did. It was almost fully autonomous to do valve turning. You could basically choose the position of the valve, and then it would automatically figure out how to turn it. That performed pretty well most of the time. It's just that we had an issue with the balancing controller, which is something that we probably should have worked on from day one. But I think they could have gotten 4 points if we had a better balancing controller.
How much of your system was shared between teams?
So that was a huge problem, very little. We had a common, I think there's a point cloud reading module, but I don't think every team used it. Camera data was using the same ROS module, but in terms of low-level control, very little was shared. Actually, one of the things that was just a huge annoyance throughout this whole process was that to do walking on flat ground, we had to switch computers to a KAIST computer and use their code to switch to walking. And then we have to switch back if we want to do something else. So that was kind of strange decision, which I don't agree with, but that's what we had to do.
So does that mean every team have their own UI for operating?
Yes. Yes.
It looked like you were only using stereo camera. Is that the case for perception?
I think some teams use the laser scanner. I know my team didn't. They used the stereo camera only. So I believe driving also used the laser sensor.
Okay, great. Let's thank Kris one more time.